Polystyrene.
Polystyrene/polystyrene is a synthetic aromatic polymer made from the monomer styrene, a liquid petrochemical. Polystyrene can be rigid or foamed. General-purpose polystyrene is clear, hard and brittle. It is a very inexpensive resin per unit weight. It is a rather poor barrier to oxygen and water vapor and has a relatively low melting point. Polystyrene is one of the most widely used plastics, the scale of its production being several billion kilograms per year. Polystyrene can be naturally transparent, but can be colored with colorants. Uses include protective packaging, containers, lids, bottles, trays, tumblers, and disposable cutlery. Polystyrene is used to make napalm-B, where it makes up about 46% of the formulation. As a thermoplastic polymer, polystyrene is in a solid, glassy, state at room temperature but flows if heated above about 100 degc, its glass transition temperature. It becomes rigid again when cooled. This temperature behavior is exploited for extrusion, and also for molding and vacuum forming, since it can be cast into molds with fine detail. It is very slow to biodegrade and therefore a focus of controversy, since it is often abundant as a form of litter in the outdoor environment, particularly along shores and waterways, especially in its foam form.
History.
Polystyrene was discovered in 1839 by Eduard Simon, an apothecary from Berlin. From Styrax, the resin of the Turkish sweet gum tree liquid Amar orientalis, he distilled an oily substance, a monomer that he named styrole. Several days later, Simon found that the styrole had thickened, presumably from oxidation, into a jelly he dubbed styrole oxide, styroloxate. By 1845, Jamaican-born chemist John Budell Blythe and German chemist August Wilhelm von Hofmann showed that the same transformation of styrole took place in the absence of oxygen. They called their substance metastyrole. Analysis later showed that it was chemically identical to styroloxate. In 1866, Marcellin Berthelot correctly identified the formation of metastyrole styroloxate from styrole as a polymerization process. About 80 years later it was realized that heating of styrole starts a chain reaction that produces macromolecules, following the thesis of German organic chemist Hermann Staudinger, 1881–1965. This eventually led to the substance receiving its present name, polystyrene. The company IG Farben began manufacturing polystyrene in Ludwigshafen, about 1931, hoping it would be a suitable replacement for die-cast zinc in many applications. Success was achieved when they developed a reactor vessel that extruded polystyrene through a heated tube and cutter, producing polystyrene in pellet form. In 1941, Dow Chemical invented a styrofoam process. Before 1949, the chemical engineer Fritz Stastny, 1908–1985, developed pre-expanded PS beads by incorporating aliphatic hydrocarbons, such as pentane. These beads are the raw material for molding parts or extruding sheets. BASF and Stastny applied for a patent that was issued in 1949. The molding process was demonstrated at the Kunststoffmesse 1952 in Düsseldorf. Products were named Styropa. The crystal structure of isotactic polystyrene was reported by Giulio Natta. In 1954, the Koppers Company, incorporated in Pittsburgh, Pennsylvania, developed expanded polystyrene, EPS, foam. In 1960, Dart Container, the largest manufacturer of foam cups, shipped their first order. In 1988, the first U.S. ban of general polystyrene foam was enacted in Berkeley, California.
Structure.
In chemical terms, polystyrene is a long-chain hydrocarbon wherein alternating carbon centers are attached to phenyl groups, the name given to the aromatic ring benzene. Polystyrene's chemical formula is C8H8N. It contains the chemical elements carbon and hydrogen. The material's properties are determined by short-range van der Waals attractions between polymers chains. Since the molecules are long hydrocarbon chains that consist of thousands of atoms, the total attractive force between the molecules is large. When heated, or deformed at a rapid rate, due to a combination of viscoelastic and thermal insulation properties, the chains are able to take on a higher degree of conformation and slide past each other. This intermolecular weakness, versus the high intramolecular strength due to the hydrocarbon backbone, confers flexibility and elasticity. The ability of the system to be readily deformed above its glass transition temperature allows polystyrene, and thermoplastic polymers in general, to be readily softened and molded upon heating. Extruded polystyrene is about as strong as an unalloyed aluminium, but much more flexible and much lighter, 1.05 grams per centimeter 3 versus 2.70 grams per centimeter 3 for aluminium.
Polymerization.
Polystyrene results when styrene monomers interconnect. In the polymerization, the carbon-carbon pi bond, in the vinyl group, is broken and a new carbon-carbon single, sigma, bond is formed, attaching another styrene monomer to the chain. The newly formed sigma bond is much stronger than the pi bond that was broken, thus it is very difficult to depolymerize polystyrene. About a few thousand monomers typically comprise a chain of polystyrene, giving a molecular weight of 100,000 to 400,000. A 3D model would show that each of the chiral backbone carbons lies at the center of a tetrahedron, with its 4 bonds pointing toward the vertices. Consider that the CC bonds are rotated so that the backbone chain lies entirely in the plane of the diagram. From this flat schematic, it is not evident which of the phenyl, benzene, groups are angled outward from the plane of the diagram, and which ones are inward. The isomer where all of the phenyl groups are on the same side is called isotactic polystyrene, which is not produced commercially.
Atactic polystyrene.
The only commercially important form of polystyrene is atactic, in which the phenyl groups are randomly distributed on both sides of the polymer chain. This random positioning prevents the chains from aligning with sufficient regularity to achieve any crystallinity. The plastic has a glass transition temperature Tg of 90 degC. Polymerization is initiated with free radicals.
Syndiotactic polystyrene.
Ziegler-Natta polymerization can produce an ordered syndiotactic polystyrene with the phenyl groups positioned on alternating sides of the hydrocarbon backbone. This form is highly crystalline with a Tm of 270 degC, 518 degF. Such materials are not commercially produced because the polymerization is slow.
Degradation.
Polystyrene is very chemically inert, being resistant to acids and bases but is easily dissolved by D-limonon, many chlorinated solvents, and many aromatic hydrocarbon solvents. Because of its resilience and inertness, it is used to fabricate many objects of commerce. It is attacked by many organic solvents, which dissolve the polymer. Foamed polystyrene is used for packaging chemicals. Like all organic compounds, polystyrene burns to give carbon dioxide and water vapor. Polystyrene, being an aromatic hydrocarbon, typically combusts incompletely as indicated by the sooty flame.
Biodegradation.
From http://www.chi-c.gc.ca/050/ document/56647/ 56647e.pdf. P-butadiene is capable of converting styrene oil into the biodegradable plastic PHA. This may be of use in the effective recycling of polystyrene foam, otherwise thought to be non-biodegradable.
Forms produced.
Polystyrene is commonly injection molded, vacuum formed, or extruded, while expanded polystyrene is either extruded or molded in a special process. Polystyrene copolymers are also produced. These contain one or more other monomers in addition to styrene. In recent years the expanded polystyrene composites with cellulose and starch have also been produced. Polystyrene is used in some polymer-bonded explosives, PBX.
Sheet or molded polystyrene.
Polystyrene, PS, is used for producing disposable plastic cutlery and dinnerware, CD jewel cases, smoke detector housings, license plate frames, plastic model assembly kits, and many other objects where a rigid, economical plastic is desired. Production methods include thermoforming, vacuum forming, and injection molding. Polystyrene petri dishes and other laboratory containers such as test tubes and microplates play an important role in biomedical research and science. For these uses, articles are almost always made by injection molding, and often sterilized post-molding either by irradiation or by treatment with ethylene oxide. Post-mold surface modification, usually with oxygen-rich plasmas, is often done to introduce polar groups. Much of modern biomedical research relies on the use of such products. They therefore play a critical role in pharmaceutical research.
Foams.
Polystyrene foams are good thermal insulators and are therefore often used as building insulation materials, such as in insulating concrete forms and structural insulated panel building systems. Polystyrene incorporating graphite has superior insulation properties. They are also used for non-weight-bearing architectural structures, such as ornamental pillars. PS foams also exhibit good damping properties, therefore it is used widely in packaging. Extruded closed-cell polystyrene foam is sold under the trademark Styrofoam by Dow Chemical Company. This term is often used informally in North America for other foamed polystyrene products.
Expanded polystyrene.
Expanded polystyrene, EPS, is a rigid and tough, closed-cell foam. It is usually white and made of pre-expanded polystyrene beads. EPS is used for disposable trays, plates, bowls and cups, and for carry-out food packaging, including the hinged lid containers popularly known as clamshells. Other uses include molded sheets for building insulation and packing material, peanuts for cushioning fragile items inside boxes. Sheets are commonly packaged as rigid panels, size 4x8 or 2x8 feet in the United States, which are also known as beadboard. Due to its technical properties such as low weight, rigidity, and formability, EPS can be used in a wide range of different applications. Its market value is likely to rise to more than $15 billion until 2020. Thermal conductivity is measured according to EN 12667. Typical values range from 0.032 to 0.038 W/mK, depending on the density of the EPS board. The value of 0.038 W/mK was obtained at 15 kg per meter 3, while the value of 0.032 W/mK was obtained at 40 kg per meter 3 according to the data sheet of K710 from Styrochem, Finland. Adding fillers, graphites, aluminium, or carbons, has recently allowed the thermal conductivity of EPS to reach around 0.030-0.034, as low as 0.029 and as such as a grey-black color which distinguishes it from standard EPS. Several EPS producers have produced a variety of these increased thermal resistance EPS usage for this product in the UK and EU. Water vapor diffusion resistance, M, of EPS is around 30 to 70. ICCES, International Code Council Evaluation Service, requires EPS boards used in building construction meet ASTM C578 requirements. One of these requirements is that the oxygen index of EPS as measured by ASTM D2863 be greater than 24 volume%. Typical EPS has an oxygen index of around 18 volume%. Thus, a flame retardant such as HBCD, hexabromocyclododecane, is added to styrene or polystyrene during the formation of EPS. The boards containing HBCD when tested in a tunnel using test method UL 723 or ASTM E84 will have a flame spread index of less than 25 and a smoke developed index of less than 450. ICCES requires the use of a 15-minute thermal barrier when EPS boards are used inside of a building. According to EPS IAICF organization, The typical density of EPS used for insulated concrete forms is 1.35 to 1.80 pcf. This is either Type 2 or Type 9 EPS according to ASTM C578. EPS blocks or boards used in building construction are commonly cut using hot wires.
Extruded polystyrene foam.
Extruded polystyrene foam, XPS, consists of closed cells, offers improved surface roughness and higher stiffness and reduced thermal conductivity. The density range is about 28 to 45 kg per meter 3. Extruded polystyrene material is also used in crafts and model building, in particular architectural models. Because of the extrusion manufacturing process, XPS does not require phases to maintain its thermal or physical property performance. Thus, it makes a more uniform substitute for corrugated cardboard. Thermal conductivity varies between 0.029 and 0.039 W/mK, depending on bearing strength density, and the average value is 0.035 W/mK. Water vapor diffusion resistance, M, of XPS is around 80 to 250 and so makes it more suitable to wetter environments than EPS.
Copolymers.
Pure polystyrene is brittle, but hard enough that a fairly high-performance product can be made by giving it some of the properties of a stretchier material, such as polybutadiene rubber. The two such materials can never normally be mixed because of the amplified effect of intermolecular forces on polymer insolubility, see plastic recycling, but if polybutadiene is added during polymerization it can become chemically bonded to the polystyrene, forming a graft copolymer, which helps to incorporate normal polybutadiene into the final mix, resulting in high-impact polystyrene or HIPS, often called high-impact plastic in advertisements. One commercial name for HIPS is Bextrine. Common applications of HIPS include toys and product casings. HIPS is usually injection molded in production. Autoclaving polystyrene can compress and harden the material. Several other copolymers are also used with styrene. Acrylonitrile butadiene styrene or ABS plastic is similar to HIPS, a copolymer of acrylonitrile and styrene, toughened with polybutadiene. Most electronics cases are made of this form of polystyrene, as are many sewer pipes. SAN is a copolymer of styrene with acrylonitrile, and SMA1 with maleic anhydride. Styrene can be copolymerized with other monomers. For example, divinylbenzene can be used for cross-linking the polystyrene chains to give the polymer used in solid-phase peptide synthesis.
Oriented polystyrene.
Oriented polystyrene, OPS, is produced by stretching extruded PS film, improving visibility through the material by reducing haziness and increasing stiffness. This is often used in packaging where the manufacturer would like the consumer to see the enclosed product. Some benefits to OPS are that it is less expensive to produce than other clear plastics such as PP, PET, and HIPS, and it is less hazy than HIPS or PP. The main disadvantage to OPS is that it's brittle. It will crack or tear easily.
Environmental issues. Production.
Polystyrene foams are produced using blowing agents that form bubbles and expand the foam. In expanded polystyrene, these are usually hydrocarbons such as pentane, which may pose a flammability hazard in manufacturing or storage of newly manufactured material, but have relatively mild environmental impact. Extruded polystyrene is usually made with hydrofluorocarbons, HFC-134a, which have global warming potentials of approximately 1,000 to 1,300 times that of carbon dioxide.
Non-biodegradable.
Discarded polystyrene does not biodegrade for hundreds of years and is resistant to photolysis.
Litter.
Polystyrene foam is a major component of plastic debris in the ocean, where it becomes hazardous to marine life and could lead to the transfer toxic chemicals to the food chain. Animals do not recognize this artificial material and may even mistake it for food. Polystyrene foam blows in the wind and floats on water, and is abundant in the outdoor environment. It can be lethal to any bird or sea creature that swallows significant quantities.
Reducing.
Restricting the use of foamed polystyrene takeout food packaging is a priority of many solid waste environmental organizations. Efforts have been made to find alternatives to polystyrene, especially foam in restaurant settings. The original impetus was to eliminate chlorofluorocarbons, CFC, which was former component of foam.
United States.
In 1987, Berkeley banned CFC food containers. In 1988, Suffolk County, New York became the first U.S. locality to ban polystyrene. However, legal challenges by the Society of the Plastics Industry kept it from going into effect until at last it was delayed when the Republican and Conservative parties became a majority of the county legislature. In the meantime, Berkeley became the first city to ban all foam food containers. As of 2006, about 100 localities in the United States including Portland, Oregon and San Francisco currently have some sort of ban on polystyrene foam in restaurants. For instance, in 2007 Oakland, California required restaurants to switch to disposable food containers that will biodegrade if added to food compost. In 2013, San Jose became reportedly the largest city in the country to ban polystyrene foam food containers. Some communities have implemented wide polystyrene bans, such as Freeport, Maine, which did so in 1990. The U.S. Green Restaurant Association does not allow polystyrene foam to be used as part of their certification standard. Several green leaders, from the Dutch Ministry of the Environment to Starbucks Green Team, advised that individuals reduce their environmental impact by using reusable coffee cups.
Outside the United States.
China banned expanded polystyrene takeout containers and tableware around 1999. However, compliance has been a problem and, in 2013, the Chinese plastics industry is actively lobbying to get the ban repealed. India and Taiwan also banned polystyrene foam food serviceware prior to 2007.
Recycling.
In general, polystyrene is not accepted in curbside collection recycling programs, and is not separated and recycled where it is accepted. In Germany, polystyrene is collected, as a consequence of the packaging law, Verpackungsverordnung, that requires manufacturers to take responsibility for recycling or disposing of any packaging material they sell. Most polystyrene products are currently not recycled due to the lack of incentive to invest in the compactors and logistical systems required. Due to the low density of polystyrene foam, it is not economical to collect. However, if the waste material goes through an initial compaction process, the material changes density from typically 30 kg per meter 3 to 330 kg per meter 3 and becomes a recyclable commodity of high value for producers of recycled plastic pellets. Expanded polystyrene scrap can be easily added to products such as EPS insulation sheets and other EPS materials for construction applications. Many manufacturers cannot obtain sufficient scrap because of collection issues. When it is not used to make more EPS, foam scrap can be turned into products such as clothes hangers, park benches, flower pots, toys, rulers, stapler bodies, seedling containers, picture frames, and architectural molding from recycled PS. Recycled EPS is also used in many metal casting operations. Rastra is made from EPS that is combined with cement to be used as an insulating amendment in the making of concrete foundations and walls. American manufacturers have produced insulating concrete forms made with approximately 80% recycled EPS since 1993.
Incineration.
If polystyrene is properly incinerated at high temperatures, up to 1000 degc, and with plenty of air, 14 m3 per kilogram, the chemicals generated are water, carbon dioxide, and possibly small amounts of residual halogen compounds from flame retardants. If only incomplete incineration is done, there will also be leftover carbon soot and a complex mixture of volatile compounds. According to the American Chemistry Council, when polystyrene is incinerated in modern facilities, the final volume is 1% of the starting volume. Most of the polystyrene is converted into carbon dioxide, water vapor, and heat. Because of the amount of heat released, it is sometimes used as a power source for steam or electricity generation. When polystyrene was burned at temperatures of 800 to 900 degC, the typical range of a modern incinerator, the products of combustion consisted of a complex mixture of polycyclic aromatic hydrocarbons, PAHs, from alkyl benzenes to benzopyrene. Over 90 different compounds were identified in combustion effluents from polystyrene.
Safety. Health.
According to a Plastic Food Service Products website of the American Chemistry Council, from 1999 to 2002, a comprehensive review of the potential health risks associated with exposure to styrene was conducted by a 12-member international expert panel selected by the Harvard Center for Risk Assessment. The scientists had expertise in toxicology, epidemiology, medicine, risk analysis, pharmacokinetics, and exposure assessment. Polystyrene is a common container for food and drinks. The styrene monomer, from which polystyrene is made, is a cancer suspect agent. Styrene is generally found in such low levels in consumer products that risks are low. Polystyrene which is used for food contact may not contain more than 1%, 0.5% for fatty foods, of styrene by weight. Styrene oligomers in polystyrene containers used for food packaging have been found to migrate into the food. Another Japanese study conducted on wild-type and null mice found that the styrene trimmer, which the authors detected in cooked polystyrene container-packed instant foods, may increase thyroid hormone levels. Whether polystyrene can be microwaved with food is controversial. Some containers may be safely used in a microwave, if labeled as such. Some sources suggest that foods containing carotene, vitamin A, or cooking oils be avoided. Because of the pervasive use of polystyrene, these health-related issues remain topical.
Fire hazards.
Like other organic compounds, polystyrene is flammable. Polystyrene is classified according to DIN 4102 as a B3 product, meaning highly flammable or easily ignited. As a consequence, although it is an efficient insulator at low temperatures, its use is prohibited in any exposed installations in building construction if the material is not flame retardant. It must be concealed behind drywall, sheet metal, or concrete. Foamed polystyrene plastic materials have been accidentally ignited and caused huge fires and losses, for example at the Düsseldorf International Airport, the Channel Tunnel, where polystyrene was inside a rail car that caught fire, and the Browns Ferry nuclear power plant, where fire breached a fire retardant and reached the foamed plastic underneath, inside a fire stop that had not been tested and certified in accordance with the final installation.